Welcome back to The Explainer. I'm really thrilled you're joining me today because, well, we're tackling some of the most highly technical alphabet soup in modern hardware engineering. If you've ever wondered what exactly makes your smartphone tick, how aerospace engineers prototype their systems, or even what powers a massive crypto mining rig, you are absolutely in the right place. We're going to completely demystify three major pillars of microchip technology: ASICs, FPGAs, and SoCs. Okay, let's dive into this.
So, here is our roadmap for today. We'll start by decoding the chip alphabet. Then, we'll look at the hardware house analogy to ground things. Next, ASIC versus FPGA explained. After that, we'll get into the system-on-chip unpacked, and finally, wrap up with the chip development lifecycle.
All right, Section 1, Decoding the Chip Alphabet, the building blocks.
Let's start by getting the full names behind these acronyms out there, just to set our baseline. First up, we have ASIC, which stands for Application-Specific Integrated Circuit. Next is FPGA, or Field Programmable Gate Array. And finally, SoC, which stands for System-on-Chip. Now, try to keep these full names in the back of your mind as we go, because they actually give away a ton of clues about what each of these chips is designed to do.
Moving on to Section 2, the hardware house analogy, making chips relatable.
You know, reading out technical names is one thing, but visualizing how they actually function, that's where the real learning happens. We're going to use a house-building metaphor here, and this brilliantly illustrates how we can think about these complex microchips. Imagine you're building a house, an ASIC. It's like a custom-built house designed perfectly for exactly one family. Every single corner, every electrical outlet, every cabinet is highly optimized for their specific routine. And because it's so incredibly custom, it's super efficient for them. But it's really difficult to modify later on. You can't exactly just knock down a load-bearing wall on a whim, right? On the flip side, an FPGA is like a modular house. Imagine a home where the interior walls and rooms can literally be rearranged whenever you need them to be. If you need a bigger kitchen today and a larger living room tomorrow, you just reconfigure it. It gives you this incredible flexibility, even if it's maybe not quite as perfectly tailored as that custom-built ASIC.
And to complete our analogy, the SoC is essentially like an entire apartment complex. It doesn't just give you a living space. It integrates literally everything you need into one single footprint. You've got the individual homes, the parking garage, all the utility management, and the security systems, all built into one self-contained location. It's a complete ecosystem all on its own.
Section 3, ASIC versus FPGA explained, the custom versus the flexible.
Let's take these analogies and actually apply them to the silicon itself. First up, the ASIC. Its core identity is quite literally in its name, application-specific. This is a chip designed to perform one specific function and one function only. The absolute defining characteristic here is permanence. Once an ASIC is manufactured and leaves that fabrication plant, it cannot be changed. It is set in stone.
So, where do we actually see ASICs out in the wild? Well, mobile processors, network switch chips, image signal processors, and crypto mining chips are perfect examples. Now, what's really interesting about this slide is the development trade-off. Developing an ASIC has a massive non-recurring engineering cost, meaning it is brutally expensive to design and it takes a really long time. But because it's custom built for exactly one job, it offers the absolute highest performance and the lowest power consumption, all crammed into a tiny chip area. It's wildly reliable, so that massive upfront cost, it pays off beautifully when you're mass-producing millions of something, like a smartphone.
Now contrast that with the FPGA, our modular house. An FPGA is a chip that users can configure and crucially reconfigure even after it's already been manufactured. You can basically think of it as the ultimate blank hardware board. You can program it to behave exactly like entirely different digital circuits right on the fly.
Because it is this amazing blank slate, FPGAs are the absolute go-to choice for hardware prototyping, research, industrial automation, and highly specialized fields like aerospace and military systems. The massive advantage here is the sheer speed of development and a much, much lower initial cost compared to an ASIC. You basically just program it and go. However, that flexibility definitely comes with a tax. FPGAs consume higher power, they generally operate at lower speeds than ASICs, and they usually require a physically larger chip to accommodate all those reconfigurable dates.
Let's compare these directly. We've actually added the SoC in here as a bit of a preview, but take a look at the time to market row. So the crucial point is how the extremely short time to market of the FPGA directly trades off against the supreme power efficiency and raw performance of the ASIC. If you need a chip for a low-volume product and you need it fast, you go FPGA. If you're going to produce 10 million units of a highly optimized device and you have a long runway to develop it, you go ASIC.
Okay, Section 4. System on Chip Unpacked, the Everything Chip.
This brings us perfectly to the SoC, the everything chip. This is the technology that is almost certainly powering the very device you're using to watch this explainer right now. Recall our apartment complex analogy. An SoC, or system on chip, integrates an entire electronic system onto one single piece of silicon. It doesn't just do one specific job. It does all the jobs required to run a complete system. To illustrate just how comprehensive this piece of silicon truly is, just look at this staggering array of components crammed into a single SoC. You've got your central processing unit and graphics processing unit, sure. But you also have memory controllers, digital signal processors, USB and PCI controllers, various communication interfaces like UART, SPI, and I2C, plus timers, dedicated security modules, and nowadays, super powerful AI accelerators. It is literally an entire motherboard shrunk down to a microscopic scale. In fact, here's a crazy bit of trivia for you. A modern smartphone SoC can pack well over 15 billion individual transistors into a piece of silicon roughly the size of your thumbnail. It's just an absolute marvel of engineering.
To make this abstract concept entirely tangible, here are the famous names you hear every single time a new flagship smartphone drops. The Qualcomm Snapdragon, the Apple A-series chips, the Samsung Exynos, and the MediaTek Dimensity. These are all real-world SoCs. They're the brains, the graphics, the security, and the communications of your smartphone, all completely unified on one single chip.
And finally, Section 5, the chip development lifecycle, how they work together.
We've been looking at these acronyms in isolation, but in reality, they're deeply connected in the engineering world. Let's move to ASIC and see how this builds into the complete chip development lifecycle. Here's the fascinating chronological journey of a microchip's design. It usually kicks off at step 1, where engineers take their brand new design and prototype it on an FPGA. Because the FPGA is like a blank, reconfigurable board, they can test things out instantly without burning millions of dollars on manufacturing. Then in step 2, they rigorously test and verify that the design actually works exactly as intended. Once it is totally perfect, they move to step 3. They take that verified design, lock it in, and manufacture it as a permanent, highly optimized, low-power ASIC. And finally, in step 4, that specific ASIC might just become one of the many specialized component blocks that gets integrated into a massive, overarching system on chip. So it goes from a flexible prototype to permanent hardware to an integrated system.
Now, let's throw a little curveball your way, just to test this newfound knowledge. This is a classic pattern interrupt that actually pops up in real-world hardware engineering interviews all the time. Is every SoC an ASIC? Take a second and think about the definitions we just covered.
And here is the aha moment. The answer is, in most commercial products, yes, mostly. An SoC is typically implemented using ASIC technology because it's custom designed for a very specific product. But the vital distinction you need to make is this. SoC is a broad concept that refers to the architectural integration of an entire system onto one chip. ASIC, on the other hand, refers to the physical implementation technology used to actually build a custom integrated circuit. It's like looking at the exact same chip, just from two entirely different angles: architecture versus manufacturing.
Let's wrap this up with a punchy, crystal-clear mental model for you to retain long after this explainer ends. ASIC, custom hardware designed for one single application, highly optimized but set in stone. FPGA, reprogrammable hardware for fast development and flexible applications. SoC, a complete, self-contained electronic system integrated onto a single chip, frequently built using ASIC technology.
I want to leave you with a final thought to apply what you've learned today. Take a look at the device you are using to engage with this explainer right now. Think about everything it's doing simultaneously for you: processing video, connecting to the internet, managing a battery, outputting audio. Based on what we've just unpacked, is it relying on the single-function raw power of an isolated ASIC or the massive, all-in-one apartment complex ecosystem of an SoC? Thank you so much for learning with me today. Keep asking great questions, and I'll catch you in the next explainer.